R has a built-in dataset called hair eye color. It's stored as two different tables, so I'm going to process the tables to get it in the right format. But what I want to do is use this data to perform a chi-square test to see if these proportions of eye colors are correct. I found these on Google somewhere. I had to adjust them slightly so that they would sum to 1. Our null hypothesis is that the distribution of eye colors in the population is what's given in this table. The alternative hypothesis is that the distribution of eye color is different from this table. We're going to assume that the people in this data set were a random sample from the population, but I think they come from some class in a school. I'm guessing this is a convenience sample. To get the table in the right form, I have to use these apply commands. This isn't something I'm going to ask you to do. It's just to get the data into the correct form because it begins as these two tables for men and women with hair and eye color. And I only want the eye colors for both sexes. And that's what I have here with this table I call I. If I take sum I, it gives me the total number of people, 592. If I multiply that by this vector of proportions, I get the expected counts for each category. The goodness of fit statistic is created from the observed and the expected counts, so we now have everything we need. If you're using R's CHISC test function, you can use the $expected to see what the expected counts were. And this is important because remember, an assumption to this test is that we have at least 5 expected in each group. The lowest expected number here is 53.28, so it's good. What I'm doing is storing these as expect, then using them to compute the statistic here. The chi-square statistic is observed minus expected squared divided by expected. This line is doing that for all 4 groups, and I'm storing this as CH. Then I take the sum of these, and that's my chi-square statistic. And you can see CH starts as these 4 numbers. Then I sum them and store them as CH. So now CH is my chi-square statistic, 32.97. I compare 32.97 to a chi-square distribution with 3 degrees of freedom. There were 4 groups. Degrees of freedom are the number of groups minus 1. The chi-square test is always in the greater than direction. I use 1 minus p CHISC. And I can get the same thing from p CHISC with lower tail equals f for false. 3.268 times 10 to the negative 7 is a pretty small p-value. We would reject the null hypothesis and conclude that the population distribution of eye colors is different from what's in this table. The p-value is so small that I can't draw it on a chi-square curve. For a curve with 3 degrees of freedom, there's hardly any area left after about 15 or so, and our statistic landed way out at 32.97. These curves go on forever, so there's always some little bit of area ahead. In this case, the area is 3.268 times 10 to the negative 7. So it's very small. And then to use R's chisk test command, you do this. You have to make sure to name this second thing P so it knows what you're talking about. But I is the collection of observed counts. P is the expected proportions. I run this and I get the same thing.